Good evening, everyone. Thank you very much for coming along. I'm going to drop these down for a true cinematic experience. Can everyone still see? If people may be wanting to make notes, can you see well enough? No response, no one can hear me anyway. So my name's Dartnell. I'm a research fellow, UK Space Agency research fellow at the University of Leicester. And the field of science I do, the kind of research I get involved in, is in a very new field of science called astrobiology, which is all about looking into the possibility of there being life beyond the Earth, looking into the science of extraterrestrial life, or to put a nice kind of pop-sci spin on it, I get paid a salary to help in the hunt for aliens, which is a lot of fun. And the actual title of my PhD, when I first got involved in this research a couple of years ago when I was still at UCL, a title of my PhD thesis, which is written in gold lettering down the spine of your thesis when you have it printed as a hardback book, is this: the subsurface cosmic ionizing radiation environment of Mars, which is a great big mouthful of a title, lots of long, grandiose, Latin-y words in it, which sounds all very impressive when you tell someone. But if I meet someone new at a party, and they hear that I'm a scientist, and they ask what my research is all about, or what my science is that I do, and I tell them that, I get left by myself in the kitchen of this party for the rest of the night. As you can, I'm sure you appreciate, I had coming to me, I deserved. So I've learned the hard way to describe the science I do as looking into the Martian death rays, as we just heard. And these death rays aren't being wielded by the Martians when the tripods come to invade the Earth. The death rays are what would be killing off any native Martian life. If life ever did get started on Mars, and we're talking about simple, primitive, bacterial-like life forms, if they ever did emerge there, and they're still on the surface of the red planet, they're being constantly bombarded by some very, very nasty, high-energy radiation from outer space, the so-called cosmic rays. And the reason that we're protected from these cosmic rays in Liverpool is because our lovely thick atmosphere above our heads, the Earth's atmospheric shield, but also a great big deflector shield that surrounds the entire planet, the Earth's magnetic field. And this helps to deflect away a lot of this charged particle radiation from space. But if you're an astronaut gone into space, beyond this protective cocoon of our world, or if you're a Martian on the surface of Mars, you're basically naked to this radiation from outer space. You receive no protection against it. So one of the big questions for, firstly, keeping our astronauts, stopping them dying when we send them to the moon for long missions, or send them to Mars to then try and bring them back alive. And a related question about how life on Mars might be able to survive this radiation environment is what I've been looking into. And you can see on the left here, this is a visualization, a kind of graphic from some of the work I've been doing with computer simulations of what this radiation from outer space is like. As this energetic radiation particle here punches straight through the thin Martian atmosphere, slams into the ground, to then trigger this great big shotgun blast, you can see in green there, of secondary radiation. And these shotgun blasts that get triggered when the radiation hits something can penetrate through meters and meters of solid rock. They're very, very energetic, very deeply penetrating. And so it's not as simple, if you want to keep our astronauts alive, it's not as simple as just putting a bit of lead lining in their spacesuit, because this stuff will go straight through that. And actually, because of that shotgun effect, you'd end up making things worse for them, not better. It's a very complex problem to try and solve and try to think about. So I've been calculating what the radiation doses are like at different depths underground on Mars from all that radiation. But as we've heard, I'm a biologist. I came from a biology background, and so I like to get my hands nice and wet and dirty doing real experiments with real life, with real cells. And I've been working with some bugs, some bacteria that I've isolated from here. This is the Antarctic dry valleys. It's right in the South Pole, right down by the bottom of the world. And it's one of the coldest, driest places anywhere on planet Earth. It's one of the most Mars-like places we've got on Earth to study. And these dry valleys are absolutely devoid of plant life and animal life. And for a long time after they were discovered, they were thought to be utterly dead. They thought to be one of the very few sterile places on Earth where life cannot get started or cannot survive at all. And it's only when you dig underground in these dry valleys, or more to the point, pick up one of the pebbles that are strewn across these dry valley floors and hit them with a hammer until they crack open, you then see a thin smear of green just under the surface of these rocks. It's green, the colour of chlorophyll, the colour of bacteria inside those rocks that have colonised them to protect and shield themselves from the cold and dry. And these hardy life forms, these hardy bacteria, have got the right kind of survival skills to survive the cold, dry environment on Mars. So I've been growing up some of these critters for Antarctica, getting them nice and healthy in the lab, growing them up to dense populations, to then smack with high doses of gamma rays to try to get them to die again, because then you know what their radiation resistance is like. You get some biological information from these experiments, from this lab work, compare it and combine it with the theoretical predictions and computer modelling, and get some kind of idea of how deep underground we'd want to go to dig to find something on Mars that might still be alive today. And some of this work of mine has been picked up quite nicely by the press, by the media. And there's been newspaper articles and the BBC News homepage, The Guardian, The Indie. Obviously my favourite was The Sun. And actually the Sun journalists did quite a good job here of, well, at least to be fair, cutting and pasting the press release we emailed to them. But they get the science story really nicely done, and talking about Martians hiding on the red planet, how they would have to be underground. But what made me want to cry but end up laughing was the picture they chose to illustrate this science article about astrobiology, which is this little green man, bug-eyed monster from Mars Attacks. And actually what's even funnier, and what did very almost make me want to cry, is just beneath that picture there's a list of related stories, links you can click onto with your mouse to be taken to another website that the Sun journalists clearly thought was important and relevant to this. And the fourth one down here is how to build your own UFO. And I really hope that I can convince you in the next 45 minutes or so that astrobiology is a science. And as a science, you learn as much as you can about life here on Earth. You design experiments, you test hypotheses, you then extend and extrapolate that information from what we know here, what we've ground-truthed on Earth, to look to other places of the planets and moons in our solar system to see whether they've got habitable environments. Could life get started there? How feasible is it to be talking about life on other planets? So I'm an astrobiologist, and this is the kind of science I get involved in. And you can sum up astrobiology as a pithy little phrase here, which I've swiped straight off the NASA website, that describes astrobiology as the quest to understand the origin of life on Earth. So where all of us came from. What was that event or sequence of events where life first got started, when our planet was still young? What do you need for the genesis of life on a young world? And then how has that life changed and adapted and diversified and evolved over deep time, over billions of years of our planet's history, to get from boring little bacteria up to big, interesting, complex metazoan life forms, multicelled animals, intelligent life like you or I. And then, of most interest to me, how is life distributed in the galaxy? Is Earth unique? Are we the only living world in the galaxy? Or perhaps is life commonplace? Is it common as muck? Is it here, there, and everywhere? And there's plenty of wet rocks out there in our galaxy teeming with life, just waiting for us to explore and discover them. And so if you sum up astrobiology in this way, as the search for life beyond Earth, you get hit immediately with another question at this party, which is, all right, Lewis, what's life then, mate? What was this thing that you're looking for? Because life on Earth is fairly obvious. It's easy to spot. We know it when we see it. It's an elephant or a ladybird or a toadstool or a tree or a weird squiggly green thing in a droplet in pond water when you zoom in with a microscope. But when we go looking for life on other worlds, we're obviously not going to be finding any Martian elephants or Martian trees. Life on Mars is going to have to be primitive and hardy, microscopic. It's going to be difficult to spot. It's going to be subtle. So what we want to be able to do is condense down from all these different examples of the diversity of life on Earth and boil it down to the very quintessence of what it means to be alive. What does a living thing have to do or have to possess in order to survive, in order to have this property of life? And you can sum up all life on Earth basically as this three-part pizza pie here. In order to be alive, in order to be a living organism, you've got to have information, and metabolism, and membrane. Now, all cells on Earth, all living organisms, carry around with them a set of operating instructions, a set of blueprints that tells them how to manufacture different bits and pieces, the components of new cells. They can put them together when it comes to reproduction. And they've got to be able to photocopy that information in one go when you pass on your information to your progeny, to your next generation. Now, all life on Earth, without exception, uses the same chemical to store its information in a digital way, in the same way that a DVD stores information in a digital way. We've got a digital information store inside each of our cells, which is, of course, the DNA molecule. And aside the fact that all life on Earth uses DNA, we all use exactly the same genetic alphabet. We spell out the information using exactly the same code. And this is by far the best evidence we have that all life on Earth, everything we see, all the trees and elephants and squiggly green things and droplets upon water, we're all descended from the same mother of life. We all share the same progenitor. We're all on the same tree of life on Earth. However, interestingly, that doesn't mean there was only one origin of life on Earth. It just happens to mean we are the only survivors, and we outcompeted everything else, or probably ate everything else. But there is the idea, there is the theory that maybe that isn't quite true. Maybe there are refuges, vestiges of other origins of life on Earth hiding in places where we haven't explored yet, or where our kind of life can't outcompete them. There's the idea of a shadow biosphere that might be waiting perhaps deep underground for us to stumble across. Now, alongside information, you need metabolism. You need a very complex and interlinked network of chemical reactions, of biochemistry, to make all those Lego bricks for you that you put together to make new cells, and to extract energy from your environment to power the mechanisms of life. And thirdly, but just as importantly, you need a membrane. You need some kind of bag or a sac around your cell. Simply stop all these other giblets from drifting away and getting diluted in the entire ocean. You need to segregate yourself from the environment and control your own internal conditions and hoard nutrients and control things. And it's these kind of things that we're designing experiments and tests to look for on other worlds. And in the case of metabolism and biochemistry, back in the 70s, we were sending experiments to Mars, the Viking probes, to look for the quirky, telltale signs of Martian biochemistry, of their breath coming out when we fed kind of nutritious soup to a sample of Martian soil and saw what kind of chemistry happened. So, and although this gives us a very good idea of what kind of thing we're looking for, I think this three-part pizza pie really overlooks the incredible complexity and sophistication of even a single cell, of the molecular machinery that's running inside all of our cells all of the time. And so I want to show you a short video now. It's only about 3 minutes long. It's been put together by some biologists working at Harvard University with computer animators. This isn't a real microscope video, but it's all based on biological fact that we've learned in our labs. And we're going to zoom in and basically take a look in the day in the life of one of our cells. This is, at the moment, the outer membrane with these hand-shaped proteins embedded in it and kind of reaching the hands up to lock with other components outside the cell so it can stick to different things. There's the shimmering sea of that membrane with all these different kind of proteins embedded in it. And we're now sinking deeper and deeper inside the cell, looking back up this great big envelope that surrounds us. And we see this intricate crisscross network of scaffolding proteins. This is just like the steel tubes that I've got right outside my building back in London at the moment to give it strength and stop it falling down. We have the same structures on a microscopic scale inside all of our cells to give them strength and stop them bursting. And these have to form together from their Lego and their components. And then when a pair of molecular scissors like this comes along and snips that chain, it falls apart again and returns those building blocks back into the pool in the cell to be used elsewhere. This is another kind of scaffolding protein kind of falling apart again. This is my favourite protein of them all. This is a molecular walking machine. These things plod along, one clown-like foot in front of the other, dragging stuff around inside the cell, taking things where they need to be to get their job done and to keep that cell alive. And we're zooming now into the very core of our kind of life, the nucleus, which is like the warehouse which stores and protects our vital information, the DNA. And that DNA is copied into a related chemical known as RNA, which is slightly chemically simpler, and we think it came first in the origin of life on Earth. At some point we were all RNA-based, and we then basically upgraded ourselves. And the way you upgrade your mobile when a new model comes out, we upgraded ourselves to being DNA-based life on Earth. Here's our molecular walking machine, just plodding through the foreground again. And then once that information in the DNA has been acted upon like a computer program to synthesize or manufacture whichever proteins are needed, those proteins are then processed and transported to where they need to be. And in this case, they're regurgitated onto the outer membrane, and they form together into these rafts. And we recognize that these are handshake proteins we met right at the beginning of the video. And they've got to where they need to be, they change their shape and reach up with their arms, and then hold hands with their counterparts outside the cell, so that this white blood cell can scurry along the inside of this blood capillary using those scaffolding proteins, and those handshake proteins, and those molecular walking machines to change its shape and ooze its way out of this capillary to go fight in a scene of infection. This is part of our immune system. It's off to go gobble some bacteria. But that is what life is, or more to the point, that's what life does. It's a process, it's a system of molecular machines all operating on each other in different ways to keep us alive. And it's that kind of quirky biochemistry we want to find as distinct from geochemistry, the chemistry of dead rocks that we might find on somewhere like Mars. And I wanted to move on now to tell you about a whole category of life forms on Earth known as the extremophiles. These are some of the hardiest survival superheroes that we discovered on our own homeworld. And we'll stop off first at this place here. This is in Yellowstone Park in North America. It's a very volcanically active region of the planet. And we have these ponds, these lakes of water that are heated underneath by all that volcanic activity. So they're bubbling and boiling hot in the middle. And they're also exceedingly acidic, with all the volcanic gases bubbling up through them and dissolving. They are boiling hot, acidic vats of volcanic water. And for scale, there's a path running alongside this volcanic lake here with some people walking along it. And if you were unlucky enough to slip off that path and splash into this volcanic lake, as someone does every couple of years, although never the same person twice, because you die exceedingly quickly and in excruciating pain as you're boiled to death in a great big vat of boiling hot acidic water. But the colours of this lake, the greens and the yellows and the oranges and the reds, those are the colours of life. They're the colours of thermophiles, or heat-loving organisms, and the colours of acidophiles, acid-loving organisms. These are bugs which have adapted to thrive and call this hellhole of a place their home, and these very, very hot and acidic conditions. So conditions which would kill us, without a shadow of a doubt. And if we look to the opposite extreme, to the psychrophiles, or the cold-loving organisms, let's imagine we've left Yellowstone Park, flown round the bottom of the planet, and we're now bobbing up and down on the waves just off the coast of Antarctica in a rubber dinghy, and we row up to the side of one of these vast icebergs we find floating there, and scrape off some of that ice, and put under a microscope just to see what we can see. And we would see something a lot like this, peering down a microscope. And obviously a lot of what we see are just chunks of ice, solid ice crystals, because we're looking at an iceberg. But because that was seawater that froze, the water that gets left behind gets saltier and saltier and saltier until eventually it doesn't freeze. So riddling their way throughout the solid iceberg are thousands of pockets and pores and channels and tunnels of very, very salty but still liquid water. And if we were to zoom in to one of those briny veins, you'd find them absolutely jam-packed, full of bacteria. They're kind of crammed in there, head to toe, like some kind of bacterial traffic jam, alive and well and doing all the things we saw in that video inside the dark depths of a solid iceberg at minus 20 degrees Celsius. So even colder than the deep freeze in your kitchen at home, something that was designed to stop stuff growing. We find these critters, we find these psychrophiles thriving under those punishingly cold temperatures. And actually, if you were to reach inside one of those briny veins and pluck out some of that life and hold it in your hand, just the warmth of your body heat would be enough to kill, to literally cook those cells, because they're adapted to sub-zero temperatures and cannot cope with anything much above the freezing point. Now, not all of these extremophiles, not all of these hardiest forms of life and most exotic forms of life on Earth are boring bacteria that you have to squint down a microscope before you can even see. There are some incredible examples of complex animal life forms living in incredibly hostile conditions or with very weird life cycles. And this one example of an animal extremophile I want to show you, I think, is also quite possibly the ugliest form of life on Earth. So apologies if you wolfed down a bit of food before coming along this evening, because this is the methane worm. This one's a girl, I think. This is her face at the front, with these tentacles sprouting out and these furry legs running down her sides. And these worms were discovered just about 15 years ago. They're completely new to science when we stumbled across them in the Gulf of Mexico, right in the bottom of the sea floor. And under the conditions down there, where it's very, very cold and very, very high pressure, water freezes and locks into the crystal structure molecules of methane gas. So you get mounds of what is known as methane clathrate ice. And these worms were spotted swarming all over these mounds and burrowing and tunneling their way down into it. And they were eating that ice. They were swallowing it and digesting it and powering themselves on what they were eating. So as well as being quite possibly the ugliest, bless you, as well as being quite possibly the ugliest form of life on Earth, this methane worm, this advanced, complex animal life form, which is not all that far removed from you or I at all in the grand tree of life on Earth, this worm can subsist by eating nothing more than frozen fart gas. It eats methane clathrate for breakfast and lunch and dinner, and it extracts all the energy it needs from that methane clathrate that it eats. It's an incredible example of the adaptability and diversibility of life on just this one planet that we live in. And the really exciting thing, the game changer about extremophiles, is when you start looking at all of them together, you look at the different ranges of conditions the different extremophiles can survive under, and you plot them on the same three-dimensional graph. This is the only graph I will show you. So if you look at pH from very acidic conditions inside the volcanic lakes that we saw, down to very, very alkaline conditions, or temperature from minus 20 inside the solid icebergs. And this graphic is even slightly out of date now, because we've now found life thriving at 121 degrees Celsius, far beyond the normal boiling point. And then salinity from pure distilled water all the way up to saturated salt solutions, like in places like the Dead Sea, which, lo and behold, isn't all that dead at all, now that we've bothered to check. And you put the different range of conditions of extremophiles we've discovered already, and you build this green boot-shaped cloud. This is the survival envelope of all life on Earth. At any point inside the shape, there's something we've already discovered surviving that particular combination of nasty, hostile conditions. And the crucial thing for astrobiology is that the survival envelope of terrestrial life overlaps with the conditions we know or we strongly suspect exist in extraterrestrial places. So the cold, acidic water beneath the face of Mars, or cold, salty, alkaline water within Jupiter's icy moon Europa, or hot, acidic water high above the cloud decks of the planet Venus. There's stuff on Earth we've already discovered that could survive on these alien worlds. It isn't all that crazy at all if you're talking about extraterrestrial life, because stuff we're familiar with could survive out there. And I want you to bear in mind now what we've been talking about so far, about what life is and what life does, and the incredible range of conditions we've now realized that life on Earth can survive under. Is that E.T. phoning home? I do get to make that joke about every other talk. Come on a tour of the solar system and look at some of the places we realistically expect there may be extraterrestrial life surviving under. And we'll start here in this desert landscape. We can see the wind has blown the dusty soil into these ripples and dunes. You can see some high altitude clouds up in the top of the sky here. But this is no place on Earth. This is the face of another world. This is what Mars would look like if you could put on your spacesuit and take a stroll across this landscape. Now, Mars is a very, very interesting case, a very interesting possibility. It's our next-door neighbour planet. And in many respects, it's the most Earth-like place we know about, or at least it was a much more Earth-like place. We know for a fact that billions of years ago, when we were first getting started here, when the genesis of life on Earth was first starting, Mars was a much warmer and wetter place. It had rivers and seas and lakes of water gushing across its face. It would have had a much thicker atmosphere to shield and blanket the world. And it would have had organic molecules, the building blocks of all life as we know it. The kind of stuff we saw in that video would have been raining down onto the surface of Mars aboard meteorites and comets in just the same way it did onto the primordial Earth, and possibly gave us a kickstart and provided the essential chemistry kit for life to get started here. So in terms of planetary habitability, Mars seems to tick all the right boxes. There's no reason to suspect that biology didn't get started here in the same time as getting started on Earth. And so we would dearly like to explore this red planet and dig around in the soil and start looking for those signs of Martian life. And one of the projects I'm involved in at University of Leicester is ExoMars. It's a Mars rover. It's an ESA, a European Space Agency rover, that's being built by us Brits, working with the Spanish and the French and the Germans and the Dutch, and the Russians have come on board once NASA and the Yanks pulled out when they realised they'd run out of all their pocket money, and they pulled out of ExoMars completely to then apparently dig a bit deeper in their pockets and find some cash they had all along to do their own mission about the same time. So ExoMars, and this is very frustrating international politics with big, expensive space missions, but ExoMars will now be an ESA Roscosmos joint mission with Europe and Russia. And most excitingly, for the first time ever with ExoMars, we're landing one of these on the surface of the red planet, a drill. So rather than scooping around ineffectually in the surface dust or poking our little finger into rocks like Curiosity is doing at the moment, we've got a 2-meter drill. We're going to be able to get a good arm's length underground and grab handfuls of Martian dirt and haul them back up to the surface from where they've been protected from the radiation underground, and then scrutinize and analyze that Martian soil for organic molecules or the signs of Martian life itself. And this mission is due for launch in 2018. As I said, it's a very, very exciting project to be working on at the moment. And if you look beyond Mars, flying out through the solar system to Jupiter, the big daddy of the solar system. But it's not the gas giant planet itself that we're interested in the possibility of life and astrobiology. It's the moons of Jupiter, the Galilean satellites. And these were discovered over 400 years ago when Galileo Galilei, his parents weren't entirely imaginative when it came to naming him. He didn't invent the telescope, but he was the first person to have the idea about what's just pointed upwards. Let's just see what's up there through our telescope. And he discovered this mini system of moons orbiting Jupiter, with Io the innermost one, and then Europa, Ganymede, and Callisto. And these are pictures we've taken more recently with probes we sent out there. And just by looking at the faces, the different faces of these moons, you spot something very, very curious. Something doesn't make sense. Io, the innermost moon, is a bright, angry, orangey yellow colour, the colour of volcanic sulphur. Io is a violent and tortured little world. It's constantly vomiting itself inside out, spewing its own innards out into its face in this never-ending cycle of hot, intense volcanism. On the other hand, Callisto, the outermost Galilean satellite, is still pockmarked and scarred with all the impact craters from billions of years ago, in the earliest era of the solar system, when all the rubble left over from the building the planets was still flying around through space and smashing down onto our moon and smashing down onto Callisto. And so Callisto hasn't changed its face in the entire history of the solar system. It's a cold, dead world, contrasting against the hot, violent world of Io. And in between, we find Europa. And we think that Europa is a lovely, warm, wet world. But beneath its face of hard, frozen water ice, there lays an ocean, a dark, alien ocean with more liquid water in it than all of the seas and lakes and rivers and oceans of the whole of the earth put together. Yet it is Europa that is the water world of our solar system and not the Earth. And as explorers, as astrobiologists, we would dearly like to land some kind of robotic probe on the outside of that shell of ice and then drill or melt away straight down through perhaps several kilometers of ice to get into that ocean, release an automated submersible, some kind of robotic submarine, to perhaps dive to the seafloor there and root around and look where signs of life might be. Perhaps trying to find hydrothermal vents, like we find supporting tiny little oases of life on our own seafloors, completely removed from the light of the sun. And if we move beyond Jupiter and the moons to Saturn, the magnificent ringed planet, and again, it's not the gas giant planet itself that we care about, it's the moon of Saturn, Titan. Now, Titan is a true giant of a moon. It's even larger than the planet Mercury, and is the only moon in the solar system to have one of these, to have an atmosphere. This is the blue sky of Titan. The problem, though, is the face of Titan, the landscape, is completely hidden from us by this really thick, hazy, orangey smog layer. This is a photochemical haze. It's basically the same kind of chemistry going on here in Titan as we get in polluted cities during the summer, like London and Los Angeles and Buenos Aires. And there's a lot of organic chemistry going on in this haze, but it stops us from seeing down the landscape of Titan to see what it's like. Until a couple of years ago, it was the largest area of unexplored real estate in the solar system because it was just hiding itself from us. And it was a couple of years ago we went to Titan, and this is again a European mission called Huygens that we built with a parachute to sink gently down to this haze layer, kind of staring between its legs and taking lots of photos for us as it emerged from this gloomy cloud bank to show us the very first images ever that we saw of the mysterious landscape of Titan. And this is what we saw on the left. This is basically the English countryside. The top of this picture here, the light areas, are the hills and mountains, the uplands of Titan. And the darker region down here is very, very smooth and very, very flat. I think this is the bed of a dried up lake. And unmistakably, undeniably, snaking their way down from these hills, joining together and spilling out onto this lake bed are networks of river valleys. And since this image was taken, we have spotted rain clouds and lakes full of fluid on the surface of Titan. This is the only place in the universe beyond the Earth where you can go on a yachting holiday. There are lakes on the face of Titan you could sail a boat on. It has winds. We have a recording from Huygens of the rustling sound of the titanic winds as the probe sank down. It's like trying to talk on your mobile phone on a windy day. It's all kind of... But the problem with Titan for life is that it is cold. It is truly nippy. It's about minus 180 degrees Celsius on the surface. And it's not liquid water that flows down these rivers and fills up these lakes. It's liquid methane. And we don't know enough yet about what kind of chemistry can get going on in liquid methane. Is it even sensible to be talking about methane-based life rather than water-based life, as all life on Earth is? And the jury is very much still out on this. It's a hot topic of current research at the moment to look into what kind of chemistry liquid methane might be able to support as a solvent, and whether we should be thinking about Titanic life or skipping over Titan and looking elsewhere. And if you look beyond our own cosmic front doorstep, beyond our solar system, and gaze out into our galaxy as a whole, this is what our Milky Way would look like if we could ever voyage beyond it and look back. There's an artist's impression of this glorious whirlpool of the galaxy that we live in. This is Liverpool, just here. And in just the last 15 years, so an enormous amount of what I'm talking about tonight is bleeding edge science. It's stuff we've only discovered in the last handful of years. And the last few years, we've now discovered well over 800 new worlds, planets orbiting other suns in our galaxy, planets orbiting other stars in the night sky. These are the so-called extrasolar planets, or exoplanets. And this is a diagram of some of the earliest ones we found that I've put together, where I've lined up their sun of these other solar systems, these alien solar systems, lined up their sun on the left and compared against our solar system on the bottom, with Mercury, Venus, Earth, that's where we are. And then Jupiter on this scale would be kind of way out here somewhere, in the outer depths of the solar system. And again, just by looking at the information, looking at what our telescopes have found, you spot something very curious. Most of these worlds we've discovered so far, orbiting other suns, most of these alien solar systems ain't much like our own. These are big, fat, chuffing planets. This one here is almost 6 times more massive than Jupiter, which is itself over 300 times more massive than the Earth. And many of these orbit very, very closely to their sun. They are scorchingly hot places, the so-called hot Jupiters, and there is no chance for water, organic chemistry, or life on these planets. And it just so happens, it makes sense when you think about it, that the easiest planets to spot are the big fat ones orbiting most closely to their star. And over time, we're spotting smaller and smaller worlds orbiting further and further away, and worlds which are in that sweet spot of orbital distances, where they're not too close to the heat of the campfire, they're not too far away and cold, but they're just right. They orbit in what's known as the habitable zone, or the Goldilocks zone of their star. And a mission that's been helping enormously, a planet hunting telescope, that might have just blinded some of you, apologies, or woken you up maybe. A telescope that's been helping enormously in a hunt for alien worlds orbiting other suns is Kepler. Now, Kepler is a bit like the Hubble Space Telescope, although unlike Hubble, Kepler never gets to look around in the night sky, never gets to look at different nebulae or galaxies or other planets. It has been commanded, it's been instructed for its entire lifetime to stare at the same tiny patch of night sky. And Kepler is looking back along the spiral arm of our galaxy. This yellow triangle here is where Kepler is peering. And this is what the Milky Way looks like when we're inside it. This is the band of stars, which is like looking back towards the centre of the galaxy and seeing your own spiral arm. And these squares here are basically the iPhone cameras, the CCD detectors, which have been arranged into an array here to allow Kepler to look at these stars. We've deliberately pointed it to a place in the night sky where there's lots and lots of stars, all crammed close together from our point of view. And Kepler was monitoring about 150,000 stars simultaneously, waiting for some of those stars to blink back at it. Because if a star blinks at you, there's a good chance it's because a planet has just passed across its face and blocked out some of that starlight. So you can use this transit method, it's called, as a very, very effective way of discovering new worlds orbiting other stars in our neck of the woods, in our part of the spiral arm of the galaxy. And this is all going very, very well until a couple of months ago when Kepler broke itself. And one of the critical components for allowing it to point very, very accurately where we want it to point in the night sky, a reaction wheel, it's a bit like a gyroscope. One of the 3 of them kind of jammed and broke, and we can't position it as accurately as we would have liked. Because the one kind of planet we've been really holding out for is a second Earth. A rocky, terrestrial-like planet orbiting a sun-like star with an orbit of exactly 1 year. So it's the right distance from the heat of its campfire. It's in the habitable zone and has conditions suitable for liquid water on its surface, for oceans and rivers and lakes, and perhaps continents flushed green with the colour of vegetation, like in this artist's impression here. And so with Kepler kind of out of the game now, it'll probably fall to another planet hunting mission, another space telescope, to find this first example of a twin of our home world. And the next step after that, after you've discovered a second Earth-like planet, is to try and characterize it, try to get to know it, to try to read the chemistry of its atmosphere from across the gulf of space and look for things like oxygen and methane in its air. Because the only way we know how to explain that would be because life has pumped it out there. And so we'll be able to find a world that's not just habitable, but is actually inhabited. There's a biosignature, a sign of life in its atmosphere. And this we hope to be able to do in the next 10, 15, perhaps 20 years. The very final slide I want to show you, I think, is perhaps the most profound photograph that we've ever taken in human history. It's known as the Hubble Deep Field picture. And it was taken by the Hubble Space Telescope a couple of years ago now, when it basically didn't have any other jobs to do. You know, the astronomers had booked out time in the Hubble Space Telescope. And so the manager of this mission said, well, all right then, let's take this most advanced and sophisticated space telescope that we've ever built, and let's point it to a place in the night sky where we can't see anything at all. Let's point Hubble between any of the stars that we can see, and let's just see what's there. So for 10 days, as Hubble whirled around and round the Earth in its orbit, it fixated and stared at the same tiny patch of the sky. This entire picture here is like your thumbnail held at arm's length. It's a tiny percentage of the whole sky around us. And it collected photons of light that have been traveling across the width of the universe that happened to stumble across its mirror and get reflected into the detector and picked up. And it built up this picture here. Now, pretty much every single fleck of light in this picture isn't a star, but an entire galaxy in its own right, an entire assemblage of hundreds of billions of stars. And we now know from missions like the Kepler Space Telescope, probably an even greater number of planets orbiting those stars in each of these galaxies. And imagine multiplying that thumbnail around the entire sky that surrounds us. So without trying to make the point too facetiously, space is big. Space is really big. And so surely, somewhere out there must be that right combination of conditions, the right kind of world with the right kind of atmosphere, the right kind of oceans, the right kind of chemistry orbiting the right kind of star for life to get started on and then evolve and perhaps even reach complex, intelligent life forms like ourselves. But as a scientist, as an astrobiologist, to be honest with you, I don't care all that much about life in a galaxy far, far away. I'd be so much more excited if life was commonplace. It was here, there and everywhere. And if it was, in fact, very close by to us. If perhaps some of the neighbouring worlds in our solar system were inhabited, a place like Mars or Europa. Because these are places we can feasibly go to in our lifetimes, first with robots and then hopefully with humans before too long, to search for signs of life. And then if we find them, to bring those life forms, bring those organisms back to the Earth, so we can study them and scrutinise them in our laboratories and kind of peer under the bonnet, if you like, to see how that life works. And I think by doing that, by finding out ways that alien life is similar to us, how we work in a fundamentally different way, but most excitingly, finding out ways how that alien life is truly alien. It's built in a different way. It does things differently. It's got different machinery inside it. I think by doing that, we'll learn an enormous amount about ourselves and our own place in this vast cosmos around us. And for me as a biologist, that is what is truly fascinating about astrobiology and the search for extraterrestrial life. So that's all I've had time to talk about. It's a bit of a whistle-stop rattle tour through a very, very diverse field of science with lots of different disciplines kind of all overlapping. I hope I've left a wee bit of time for questions, and I will put in one final shameless plug for two very good books. Life in the Universe Beginner's Guide, or My Tourist Guide to the Solar System, which is an illustrated children's book. And through no coincidence, I'll be honest, there are one or two copies of those along with me. So if you wanted to read a bit more about this science of astrobiology, you can do so. But thank you very much for your attention. Cheers.